In today's video, we're going to explore how the internal energy of an object is connected to its temperature, using the concept of specific heat capacity. Let's start by understanding a few essential terms. Internal energy refers to the total energy stored by all the particles that make up a substance or a system. We typically divide this internal energy into two main components, the potential energy stores and the kinetic energy stores. Potential energy includes forms like gravitational and elastic potential, but since these aren't really affected by temperature, we can mostly ignore them for the purposes of this explanation. What we do need to focus on is the kinetic energy of the particles, which is directly linked to temperature. Every time a substance is heated, energy is transferred to the kinetic energy stores of its particles, which increases their internal energy. This increase in internal energy is what we observe as a rise in temperature, since temperature is effectively a measure of the average internal energy of the substance. So, in simple terms, the more internal energy a substance has, the higher its temperature will be. However, not all materials respond the same way when energy is added. Some materials need significantly more energy than others to raise their temperature. For example, to heat 1 kilogram of water by 1 degree Celsius, we need 4,200 joules of energy, whereas heating 1 kilogram of mercury by the same amount only takes 139 joules. These values are known as specific heat capacities, and they tell us exactly how much energy is needed to increase the temperature of 1 kilogram of a substance by 1 degree Celsius. The same number also tells us how much energy will be released when the substance cools down by 1 degree. So, each time our 1 kilogram of water cools by 1 degree Celsius, it releases 4,200 joules of energy to its surroundings. Now, we can express this idea mathematically using an equation. The change in internal energy is equal to the mass of the substance multiplied by its specific heat capacity and then multiplied by the change in temperature. Here, the triangle symbol stands for change, and the Greek letter theta represents temperature. To see this equation in action, let's solve a quick example. Suppose we want to find the final temperature of 800 grams of water that starts at 20 degrees Celsius after it has absorbed 20 kilojoules of energy. We are told the specific heat capacity of water is 4,200 joules per kilogram per degree Celsius. First, we need to isolate the temperature change in our equation, so we divide the energy by the product of the mass and specific heat capacity, giving us change in temperature equals energy divided by mass times specific heat capacity. Next, we convert all units to the standard ones. 800 grams becomes 0.8 kilograms, and 20 kilojoules becomes 20,000 joules. Plugging these into the formula, we calculate a temperature change of approximately 5.95 degrees. Adding this to the initial 20 degrees gives us a final temperature of 25.95 degrees, which we can round to 26.0 degrees if we want to give our answer to three significant figures, as a standard practice. It's worth noting, however, that in real-world scenarios, the temperature might not increase this much because some energy would inevitably be lost to the surroundings, mainly in the form of heat. So if you're planning to carry out this experiment in a classroom setting, it's a good idea to use a lid and insulate the container properly to minimize heat loss. That wraps up everything for this video. So if you found it helpful, please give it a like and subscribe to the channel, and we'll see you again soon.